Here we have a problem. The equation that is incorrect, that we have to find. Total 4 expressions are there. Okay, so all are related to molar conductivities at infinite dilution. So this is based on Kohlrausch law, that at infinite dilution all the cations and anions, their molar conductivity, that will have independent contribution. It will not depend on the conductivities of its counter ion. Okay, so here if we look at the first equation, we have NaBr molar conductance and NaCl. So basically here sodium, both the cation are common, and as we are subtracting it, so Na will be cancelled. So what will be remaining? It is Br minus Cl. Now look at the right hand side. Here we have K both common. So potassium plus, both the ions will be cancelled, and what will be remaining? Br minus and Cl minus. So both sides it is actually Br minus minus Cl minus. So that is why this is correct. Now, okay, then in the second one we have KCl and NaCl. So here we have the anion common. So anion will be cancelled. So what will be remaining? K minus Na. So here in the right hand side Br is common. So anion will be cancelled. So here also it is K minus Na. So this equation is also correct. Next we have H2. Now H2O means what? There is H plus and HO minus, both cation and anion. Now look at the right hand side. Here we are adding HCl and NaOH. That means H plus, Cl minus, Na plus, HO minus, all these ions will be there. But we are subtracting NaCl. That means Na will be cancelled, Cl will be cancelled. What will be remaining? H plus and HO minus. So both sides are same. So this is also correct. So only incorrect is the last one. Now for the last one, if we consider this equation at the left hand side, that is lambda m naught NaBr lambda m naught NaI. So this is actually Na plus Br minus, then minus of Na plus and I minus. So here Na will be cancelled. So this will be remaining. And if you consider the right hand side equation, that is this part, if you consider, here what you will have? Just break it. It is K plus Br minus, then Na plus Br minus. So these two will be cancelled. So remaining these two are K plus and Na plus. So which is not matching with this side. Okay. So that is why this cannot be equal to the right hand side. So ultimately it will be not equal. So we have to find out which equation is incorrect, and the last equation is incorrect. So correct option will be option 4. NaBr minus NaI, right hand side KBr minus NaBr. Okay. Next we have another problem. So here dissociation constant of N-butyric acid. Okay, this is weak acid. So that is why dissociation constant is given. Molar conductivity at infinite dilution, that is lambda m naught or lambda m infinite, that value is given. What you have to find out? Specific conductance, that means kappa. So when we have discussed application of Kohlrausch law, then we have seen that how applying this law we can find out dissociation constant of any weak electrolyte. Okay. Now as here dissociation constant value is given, so we don't have to find that, but as this value is given, so right now we have to find out specific conductance, but opposite may be the case, that is specific conductance is given, dissociation constant we have to find. So different types of numericals may be possible. Okay. So as here dissociation constant value is given, so first of all, if we want to know what is alpha, that is degree of dissociation, because degree of dissociation it is related to dissociation constant. So if alpha is known by application of this equation, that is lambda m divided by lambda m naught. Okay, lambda m naught is given, alpha is unknown, lambda m, that is also unknown. Okay, so this variable must be known. that is one of these two unknown are here. Okay, now alpha can be easily find out from this dissociation constant. Why? Because concentration is also given. So first of all we will write the equation as if N-butyric acid is actually 4 carbon then carboxylic acid, but that is not required. Simply write Ha, weak acid dissociated as H plus and A minus. So initially the concentration suppose is C, these two will be 0, and if alpha is the degree of dissociation, remaining amount of Ha, that is undissociated Ha, will be C minus C alpha. So C alpha is the amount of Ha which is dissociated. So the amount of H plus will be C alpha and A minus, that is also C alpha, because from 1 mole of Ha we will get 1 mole of H plus, 1 mole of A minus. So dissociation constant K, that will be equal to concentration of H plus A minus divided by undissociated H. So C alpha multiplied by C alpha, C common 1 minus alpha. Now here alpha is very small compared to 1. So that is why 1 minus alpha, it is almost equal to simply 1. So this part you can consider as if it is 1. So what in the right hand side remaining, K is equal to C alpha square. That means alpha is K by C root. Now put the value of K. K is given 1.6 10 to the power minus 5. Concentration is 0.01. So here we have 10 to the power minus 2 and here minus 5. That means it will be 1.6 10 to the power minus 3. Now you can also write it as 16 into 10 to the power minus 4. So the calculation will be easier. So 16, its root will be 4 and 10 to the power minus 2. So this is basically 0.04. So this is the value of alpha. So now as we know the value of alpha, we can easily calculate this one. Okay, that is lambda m. So lambda m naught is given. So lambda m will be alpha into lambda m naught. Alpha is 0.04 and lambda m naught value given is, look at here, 380 multiplied by 10 to the power minus 4. Okay, so this 0.04, it has no unit, so we will have same unit, and this value is actually 15.2. Okay, how we are getting it, that we have to show, because here the unit is S meter square per mole. So if we first calculate, that is if you simply multiply 0.04 with 380, the value that you will get is 0.00152, and here the unit is S meter square per mole. But what we will do, we will convert it to centimeter. So when you are converting centimeter, that means meter square is here. So if we want to convert it to centimeter, as there is square, if it is simply meter to centimeter, it is 10 to the power 2. But as it is meter square, it will be 10 to the power 4. So when we multiply 10 to the power 4, what will be the value? It will be 15.2. Now the unit is S centimeter square per mole. Okay, and finally we can calculate kappa, because kappa is how it is related to lambda m. It is related to lambda m by this relation divided by concentration. Okay, which is in given here in molarity, because this is molar conductance. If it is equivalent conductance, then the concentration it must be normality, but here it is molar conductivity, so 0.01 molar, that is okay. So kappa is equal to lambda m multiplied by 0.01 divided by 100. So if we put here 15.2 1000. Then the value of kappa that we will get is 1.52 into 10 to the power minus 4 s centimeters per centimeter. Why? Because here the unit of kappa is s per centimeter. Okay, so as we have used the unit for lambda m s centimeter square per mole, so obviously it will be s centimeter square, s centimeter inverse. Okay, now from s centimeter inverse, finally we will again convert it to meter inverse. Why? Because if you look at the options, all are given in meter inverse, not centimeter inverse. Okay, so per centimeter, if this is the value, obviously per meter it will be higher value, right? So that is why we will multiply with 10 to the power 4. Okay, sorry, 10 to the it is centimeter, it is not square, so it will be simply 10 to the power 2. So 1.52 multiplied by 10 to the power minus 4 multiplied by 10 to the power 2, simply 2, because you are converting from centimeter inverse to meter inverse. So as it is inverse, it is not 10 to the power minus 2. Normally what we know, when from small unit we are converting to larger, normally what we do, we divide by 100 or 1000 whatever, but here we are having centimeter inverse and we have to convert it to meter inverse. So that is why multiplied by 10 to the power 2. So ultimately the value is 1.52 10 to the power minus 2 s meter inverse, and it is matching with which option? It is matching with this option, 1.52 into 10 to the power minus 2 s meter inverse. Okay, so in this way we have to solve the problem. So here we have seen that how this application of Kohlrausch law, because dissociation constant, it is related to lambda, and lambda is also related to dissociation constant is related to alpha, and alpha is related to this ratio, that is lambda m by lambda m naught. So that is why we can solve this equation, this question. Next we are starting quantitative aspects of electrolysis. Now electrolysis we have already discussed in the, that is before Kohlrausch law, and that is galvanic. When we have discussed galvanic cell, mainly at that time we have discussed the other cell. Okay, because there are two types of cell we know. In galvanic cell we convert a chemical energy to electrical energy, which is spontaneous reaction. But if it is not spontaneous reaction, then now we will apply electrical energy so that we can do this non-spontaneous reaction easily. Okay, so that process is actually electrolysis. But what is quantitative aspect? Quantitative aspect means if we are doing electrolysis for some compound, then what will be the amount of the products that will be obtained at cathode or anode, that quantity how we can predict. So for that there is some specific laws that we have to know. But what is electrolysis? This is actually a process in which electrical energy will be converted to chemical energy, because here the reaction that we are using, that is not naturally possible. Okay, this is not impossible reaction, but as we are applying electrical energy, that means we are basically forcefully doing the reaction. And the device that is used, that is the cell, and it is known as electrolysis. That is, the process is known as electrolysis. Now Faraday investigated this process quantitatively, and what he found, that during electrolysis the quantities of substances liberated at the electrode, that is at anode and cathode, it depends on some factors. So the factors are quantity of current that we are passing, then the time duration of passing the current, and it must be uniform rate. So time, quantity of current, and charge on the ions being deposited. So suppose there is some cation having charge 2 plus, 3 plus, or plus 1, or anion having charge minus 1, minus 2. So this charge is also important. Why it is important? Because as we are passing electricity, that means what? Electron movement is there. Now depending on the charge, different number of electrons will be involved. So that is why here charge is important. Because suppose if it is sodium plus ion, 1 electron will be required. But if it is aluminium 3 plus ion, obviously we have to provide 3 electrons. So number of electron is different, that means current will also be different. That is directly related to electron number. So that is why current, time and charge, these three things are important. The amount, that is the quantity of final product that will be deposited at cathode and anode, that will be directly dependent on these three factors. So laws of electrolysis, which is done by Faraday, this is actually the relationship between the quantity of electric charge passed through an electrolyte and the amount of substance that is deposited at the electrode. So the laws of Faraday are related to all this. Okay. So there are basically two laws. The first law, the mass of the substance that will be deposited. So if it is solid, obviously it will be deposited, but suppose if it is gas, then we will say that it is liberated at any electrode. It may be cathode, it may be anode. It is directly proportional to the amount of charge passed. So W is the amount or quantity of the substance that will be produced, and Q is quantity of electricity. So W is directly proportional to Q. Now quantity of electricity that is related to current and time by this relation, that is I into T. So I is basically current and T is basically time. So when you multiply current and time, you get the total charge, that is electricity. So the charge unit is coulomb, current unit is ampere, and remember time is always expressed in second. If it is given in meter or hour, then you have to convert it to second. It is the relationship is such that always we have to use second unit of time. So in place of Q we can write IT. So W is also proportional to IT, and if we remove this proportionality sign, there will be a constant which is Z. Now Z is also it has some significance, because when I and T both are 1, okay, when I and T both are 1, that means when Q is 1, then W will be directly equal to Z, right? Now I and T both 1 means what? That is, you are supplying 1 ampere current for 1 second, then only there will be 1 coulomb of charge, and when there is 1 coulomb of charge, then only the amount that is produced, that is actually equal to Z, which is constant. So Z is obviously proportionality constant, that you can easily understand, and it is known as electrochemical equivalent. So as I have said, when 1 ampere current is passed through a solution in 1 second, that means what? 1 coulomb of charge, 1 C, then the deposited mass of the substance or the electron, that will be equal to this Z. This is Z. Or another way you can say that it is the mass of the substance in gram deposited or liberated for gas when we are passing 1 coulomb of charge, which is same thing we are saying but in a different way. And remember, very important thing, that sometimes electricity amount is so large, that is Q, this Q is so large that we have specified there is a specific unit for large quantity of electricity. So there is a larger unit when the amount of electricity is very large, and that is, if we consider this quantity, that is 96500, very high value of charge in coulomb, that will be equal to 1 Faraday. So why we have introduced this new unit? Because when you are dealing with this type of very high value, it is difficult to that is, for practical purpose, it is very difficult to handle. So that is why if we have fixed some unit like this, so now the number will be reduced. Okay, so it will be easy for us to handle when we will solve the numericals. So this is 1 Faraday. You have to remember this value. This is 96500 Coulomb. Now here, for your convenience, I have mentioned these tables. So you will see that these are the basic electrical variables, and frequently all these will be reduced. So these units we have already seen, that is resistance, conductance, okay. But here this time, which is always in second, then charge symbol is Q, but unit is Coulomb, that is C. Current is I, but it will be ampere. So if it is said that 1 ampere current, that means 1 I current, and voltage V, then power P, which is having unit watt. This maybe you can see sometimes the use of it. Energy W, which is obviously in joule. Resistance in ohm, and for conductance it is Siemens or mho, or another unit is also there, which is simply ohm inverse. Okay, all are same. You can use any of them. So this table, try to remember, because there are so many variables, there is a chance that you will be confused. So that is why if you maintain some table, so at a glance, that is in a single glance, you can see all the symbols and the corresponding units. So this is the first law. Now what about the second law? So the second law, it is saying that when same quantity of electricity is passed through the solution of different electrolyte. So suppose there are 2 to 3 or 4 electrolyte that are connected in series. Fine. So in that case, the masses of the substances that will be liberated or deposited, depending on it is gas or solid, at the electrodes, this amount will be directly proportional to the equivalent masses of the substance. So suppose in the first you have 2 cell you have connected, that is different electrode connected in series. So in the series there are 2 systems. So obviously in the first case, W1, that is the amount deposited, that is directly proportional to equivalent mass, that is equivalent weight, and in the second system W2 is also equivalent to E2, directly proportional to E2. So from these two relation we can say that the ratio of W1 by W2, that will be equal to the ratio of E1 by E2. Similarly, if there is another system, suppose W3, then W3 will be proportional to E3, and in that case you can write W2 by 3 is equal to E2 by E3. Okay. Now look at this picture. Here we have 3 systems. All are connected in series. The first one, electrolyte, we have taken NaCl, then we have taken copper sulfate, and the last one, aluminium chloride. Okay. So here sodium plus cation, that will accept 1 electron because charge is simply +1. But copper sulfate, as the charge is 2+, it will accept 2 electron to be reduced to copper, and aluminium 3+ will accept 3 electron. Okay. So now equivalent amount, that how we will find? We know that atomic weight of sodium, this is 23, right? So if we want to know the equivalent weight from atomic weight, then we have to, that is for equivalent weight, it will be the weight of sodium divided by 1, because here valence is 1, because only 1 electron is involved. Similarly, equivalent weight of copper, that will be the atomic mass of copper divided by 2. Okay. So atomic mass of copper divided by 2, if we do, you will get the value 31.75. So this is the equivalent weight of copper. And in case of aluminium, it will be atomic mass of aluminium, that is 27 divided by 3, because here valence is 3 electron involved. So 9 will be the value, 27 by 3, 31.75, and here it is directly equal to atomic mass because only 1 electron involved. So when 1 electron involved, the molar mass, that is atomic mass, and equivalent weight, both will be same for this element. So suppose we are passing X moles of electron, that means we are passing same quantity of electricity. These two things mean the same thing. You are passing same quantity of electricity, that means we are passing same number of electrons. So if it is X moles of electrons passed through the 3 cells, then the mass of these 3 metals that will be deposited, it is 23 into X. That means equivalent weight multiplied by the number of moles. Okay, then for copper it is equivalent weight multiplied by the number of moles, equivalent weight multiplied by the number of moles. So here just use this equation for sodium and copper system, that is the first two. If we use it, what it will be, W1 is 23 into X, this is the mass deposited, W2 is 31.75 X, and what is the equivalent weight of sodium, it is 23, and equivalent weight of copper 31.75. so X cancel, both side are actually same. Okay, so this relation we are getting from second law. Now this relationship, that is number of electron into equivalent weight, that is equal to the quantity of electricity. We will focus on this part in the next slide. But before going to that, let's combine these two laws. So from the first law, what we have seen, W is equal to ZIT from the first law, and from the second law we are getting this relation. Now put in place of W1 Z1 IT, and in place of W2 write Z2 IT, which is from first law. So IT will be cancelled. Ultimately what you are getting, Z1 Z by Z2 equal to E1 by E2. That means we can write Z is proportional to equivalent weight. Okay, and if we want to remove this proportionality sign, there will be a constant Fz equal to E. So remember this relation, Z is equal to E by F. F is 1 Faraday, which is equal to 96500 coulomb of charge, larger unit of charge. So now we have this deposited mass, that is equal to number of electrons multiplied by equivalent weight. So in the previous slide, what we have seen, in case of copper, 2 moles of electron, suppose if it is involved, then the equivalent weight, which is 31.75. That means when we are passing 2 moles of electron, there will be 2 into 31.75 gram of copper that will be deposited. Fine. Now the charge which is possessed by 1 mole of electron, that you can calculate easily. Why? How? It is simply multiply the charge of single electron, which is 1.6 into 10 to the power minus 10. This is the charge of single electron. Now 1 mole of electron means what? There is Avogadro number of electrons, because 1 mole of any substance is always equal to Avogadro number of that particular substance. So if you multiply these two numbers, basically you will get 1 Faraday. That is the significance. So this is 1 Faraday. Okay. So this relationship is important, and how you can get it, that is W is equal to Q by 96500. Q means charge. So just compare the two sides. W is equal to number of moles into E, and W equal to Q by 96500 into E. That means this is nothing but number of moles. Okay, and see how we can calculate it. It is very easy to do. So suppose we know that 96500 coulomb, when it is passed, then it is actually for 1 mole of, it is equivalent to 1 mole electron, right? That we have just seen here. Now suppose if the charge in any system, it is the amount is small q. So for small q coulomb of charge, the corresponding number of moles will be first 1 by 96500, then multiplied by q. So this is the number moles of electron. So here that is written. So in this way we can calculate it. So whenever you will get that is, if it is mentioned that suppose X ampere current is continued for 1 minute, that means 60 seconds. So ampere into time, what you will get? You will get the value of Q or small q, that is the total charge. Next, what you will do, you will divide it by 96500. So directly you will get the number of moles. Okay, 96500. So this is also Coulomb unit, this is also Coulomb, it will be cancelled. Number of moles, there is no unit. Now when we know what is the number of moles, you can easily calculate what will be the quantity of the substance. So suppose if it is copper 2 plus, so for copper 2 plus, it accepts 2 electron. We are getting copper. So when you are getting 1 mole electron, when you are getting 1 mole copper, then you have to supply 2 electron. Okay, 2 mole electron. So the relationship is 2:1. Okay, so here if the number of moles, suppose you have obtained the value is 10. That means when 2 electron involved, you are getting 1 mole copper. So when 10 will be involved, you will get 5 moles of copper, that is half of it. So in this, and when we know the number of moles of copper, you can calculate the corresponding weight by multiplying it with its atomic mass. Okay, so in this way we solve numericals. So here we have another definition. The quantity of substance which is deposited when 1 Faraday of electricity, that is this value, is passed through an electrolyte, that is known as gram equivalent. Okay, so when you are supplying 1 Faraday, basically you are supplying 1 mole electron, right? That we have seen already. So when you are supplying 1 mole of electron, this value will be 1, that means W is directly equal to E. Okay, so this is also known as gram chemical equivalent. Okay, or this is actually the equivalent weight. Fine. So when you will solve numericals, all these calculations you will right now you are seeing so many things together, so you may be confused, but the more you will solve the numericals, the idea will be completely clear. Okay, there is nothing complex here, and numericals from this chapter is very common. You will get a lot of problems from this chapter. So let's solve a problem. 3 ampere current was passed through an aqueous solution of an unknown salt of PD, palladium. The element is simply given, but we do not know what is the salt. So we do not know what is the valency of PD. Time given 1 hour. Amount of PD N plus. N unknown. But weight of PD N plus, that is given, which is deposited at cathode. So we have to find N, and it is an integer type of problem. So N value, it will be some integer because it is the oxidation state of palladium. Atomic weight of palladium given 106.4. So first of all, as time and current both are given, we can easily calculate total charge. According to the relationship, Q equal to IT. 3 into, now see, this is in hour, so we have to convert it to second. So 1 hour is 60 minutes and 1 minute is 60 seconds, so it will be 60 and 60. Okay, now this is the total Coulomb charge. Now to find out number of Faraday, which is nothing but number of electron, right? Because 1 Faraday is equivalent to 1 electron. So this will be equal to the charge that we have from this 3 ampere current for 1 hour divided by 96500. Okay, so from this you can get 0.112 Faraday, or this is the number of moles of electron. Okay, now as we have PD salt, so suppose the here oxidation state is N plus, that means if you want to get PD, obviously you have to supply N number of electron. So when it is 2 plus charge, then you have to supply 2 electron. Similarly, if it is N plus charge, you have to supply N number of electron. Okay, now N moles of electron, it means what? n moles of electron is equal to basically n Faraday of charge. Okay, so n Faraday of charge when we are supplying, then this amount, that is atomic weight of palladium, that will be deposited, because for 1 mole of PD you have to use n moles of electron, and when you are using n moles of electron, it is basically you are supplying n Faraday of charge. So when we are supplying n Faraday of charge, basically the corresponding atomic weight, because 1 mole of PD will be deposited. So now we can write 106.4 gram PD will be deposited if you are passing NF current, that is NF charge. So this amount when deposited, what is the corresponding Faraday? It will be NF by 106.4 multiplied by 2.977 Coulomb charge, and this is actually it will be in Faraday unit. This is not you don't have to put it here. This is simply the unit here, that is in Faraday. In Faraday. So this will be equal to 0.0228 N, and unit is Faraday. Okay. Now from this current and time we have already calculated what is the Faraday, and by applying another that is from this equation we have also calculated what is the Faraday. So these two values are basically same. Okay, so 0.028 N. Both are having Faraday unit, so N will be okay. So here oxidation state of palladium is 4+. Integer type of question, so that is why this is the answer. Okay. Concept of overpotential in electrolysis. So we have already discussed electrolysis, and electrolysis of NaCl under two conditions we have discussed already. One is molten NaCl. So in case of molten NaCl, basically there is no water. Okay, only Na plus ion, Cl minus ion is there. But when you are there is electrolysis of aqueous NaCl, basically water is also present. So as water is also present, that means now in the medium there are two types of cation, two types of anion. So cation will be H plus, Na plus, anion will be HO minus, Cl minus. So when it is molten NaCl, there is no competition between two cation. But now as you have water molecule also, so there will be competition between these two cation. Okay. So now which cation will be reduced, that will be decided completely by the these values of reduction potential for all these systems. So that is why I have here this electrochemical series, so that directly you can see the values. So for sodium plus, just see, this is the value. Okay, and for H plus, now see, H2O is very weak electrolyte. Okay, it like NaCl it will be 100% dissociated, but H2O like NaCl it will not be 100% dissociated. So that is why we will write H not in the form of H plus, we will write it in the form of H2. Okay, so if we look at the other values, that is water where reduced to, sorry, it is, look at the system, water is accepting electron and it is reduced to H2 and HO minus, right? So this equation also we will consider, and its reduction potential value is minus 0.83. And we know that higher is the negative value, that is as we are moving down, more negative is the value, because all these are below 0. So more negative value means its reducing capacity is very high. That means it can easily feed electron to other system. It can easily lose electron and it can give to some other system. Okay. Now as here sodium plus is more electronegative, right? Sorry, sodium plus is more negative compared to this one. So that means sodium plus, it will have higher tendency to reduce. Next, see the probable reactions at cathode. Okay, so at cathode there will be reduction of sodium plus, it is accepting electron, it is sodium, and as I have said that we will not write water as H plus, we will write it simply as water. So it is accepting electron. So just imagine that in H2O there is H plus and HO minus. So HO minus is intact, but H plus after accepting electron to H2, it will be half hydrogen. Sorry, it is 2H2. So there will be formation of H2 and sorry, it is okay. So from H2O there is H plus and HO minus, but H plus is reduced to H2 and HO minus is intact. So this is basically the reduction of H plus. Now see, based on cell potential, water should be preferentially reduced over sodium ions. Okay, because sodium ion, it has more reducing capacity. That means it will be itself oxidized. Okay, so here among these two system, as this value is high compared to this one, so water, this system should occur. Okay, and actually that is experimentally that is also found. So here we do not have any problem, but the problem is in the anode, and that is related to overpotential. Here we do not have any overpotential concept. We will come to what is overpotential, but before that we have to understand when the question of overpotential arises. So in cathode there is no problem. According to the chemical series, these two values if we consider, obviously as it is higher position, that is water, so water will its accepting tendency of electron, that will be high compared to sodium plus. Now look at anode. Anode, Cl minus will be oxidized to chlorine and it will lose electron, 2 electron. And here H2O, now H2O, it is not written as HO minus, because you may think that as it is anode we have to consider HO minus, but just in case of cathode we have not written H plus. Here also we will not write HO minus because it doesn't remain in the form of HO minus, it is weak electron. Okay, so just think that there is presence of H plus and HO minus. Now H plus is intact, H plus there is no change, but HO minus will be converted to oxygen. That means in HO minus, oxygen has, what is the oxidation state? It is -2. HO minus, overall charge is -1. But if you individually consider H is +1, oxygen is -2, that is why excess charge is here. So from -2 state, now it is converted to 0. That means it is oxidation. Just like chloride is oxidized to chlorine from -1 to 0. So oxygen from -2 to 0. So this is also oxidation. Now look at the corresponding values. For Cl minus 1.36 and for water 1.23. So here we know that electrochemical series odd values are given in the form of reduction potential. But when we write the anode reaction, obviously we will write the reverse reaction because oxidation is going. Now based on cell potential, water is having lesser value compared to 1.36 and here oxidation is going on. That means the capacity to lose electron. So higher is the capacity to lose electron, that system will be actually present in anode. Now as chlorine is present at higher position compared to water system, so its electron giving tendency that will be very low. Okay, so this reaction should not occur. This reaction should occur. But so based on cell potential, water should be preferentially oxidized over chloride ion. But actually what happens? The opposite happens. So from theoretical discussion, we cannot explain this, because according to our discussion, according to this logic of electrochemical series, chloride should not be oxidized. Here H2O should be oxidized to oxygen. But why chloride is oxidized? Now we will see what is overpotential. So experimentally observed product is chlorine, not oxygen, and this is due to the phenomena overpotential. Okay, so what happens? The discussion that we are doing on the basis of electrochemical series, that is actually thermodynamic concept. But when we consider the kinetic approach, what happens? Then the activation energy for the process is so high that the reaction, though thermodynamically possible, but it is not possible kinetically. So it happens sometimes that some of the electrochemical processes, although it is feasible thermodynamically, as it is clear from the electrochemical series, it is so slow kinetically that at lower voltage these do not seem to take place. And if you really want the reaction to take place, you have to apply some extra potential, and that is known as overpotential, which makes the process more difficult to occur. So because of this overpotential, that is excess voltage we have to give, so that is why if we are not supplying it, the process will not take place. So ultimately, what is the definition of overpotential? It is a potential difference, or you can say over voltage also, similar thing, between a half reaction's thermodynamically determined reduction potential. Okay, so for oxygen water system, what we have seen from the electrochemical series, that the thermodynamically determined reduction potential is 1.23, but actually when you are doing the reaction practically, then because of the kinetic reason, the actual potential is higher than that. So this difference between these half reactions thermodynamic determined reduction potential and the potential at which the redox event is experimentally observed, this difference is overpotential or over voltage. Okay, so because of this reason, chlorine is liberated, not oxygen. So probable reactions at cathode, these two, but among these, this one is occurring, not this one, and probable reactions at anode, this one is occurring. Because of overpotential, this is not. So ultimately, when you are doing the electrolysis of aqueous NaCl, what will be the net reaction? This is the net reaction. So you have NaCl, you have H2O, and in the cathode and anode there will be production of these two. Okay, this is anode, this is cathode, and as these two reactions are not occurring, okay, that means what? Here HO minus, that will be remaining, because HO minus is not oxidized to O2, it is still there, and Na plus is also present because this reaction is not occurring. That means Na plus will be in the medium, HO minus will also be medium. So this Na plus and HO minus together will make NaOH. So this is also the application of this electrolysis. You can say that you can synthesize sodium hydroxide by the electrolysis of sodium chloride, and obviously it is aqueous NaCl electrolysis, because if it is molten NaCl, then there is no water and no question of H plus ion, HO minus ion or overpotential. Okay, so when we are doing electrolysis of aqueous NaCl, we can produce solid NaOH, which will be produced. And here all the products, if we see, chlorine gas, hydrogen gas and sodium hydroxide. Okay, now related to this electrolysis of NaCl, aqueous NaCl, we have a problem here. So we are doing electrolysis of aqueous NaCl, and it is asking what volume of chlorine, because it is gas, so volume is used, in in the time that it takes to liberate 5 liters of hydrogen. So the time under which you are getting 5 liters of hydrogen, if you are applying the same time, what will be the amount of chlorine? You can assume both gases at STP. See, it seems very difficult because as if you have to calculate the time, then accordingly you have to do the calculation, but actually it is not so, because as you have seen in the previous slide, what is the net equation? Just look at the last equation, 2 NaCl plus 2 H2O. It is a balanced equation, right? You are getting 1 mole of chlorine, 1 mole of H2. So when 1 mole of H2 is produced, then in the same time 1 mole of chlorine will be produced. So this is actually same number of moles, and we know that for gas, number of moles at STP, number of moles, that is directly proportional to volume, and as it is mentioned STP, that means both the gases, they are at same condition. So we can easily say that number of moles, that will be equal to that will be proportional to volume. So whatever will be the volume of hydrogen, it will be same for chlorine. So basically the answer is 5 liters. Okay, because the number of moles for both the gases are same. But still we will solve the problem in detail. At anode, the reaction that is taking place, 2Cl minus. Suppose if you can't remember the net balance reaction, then you can do in this way. And try to keep the number of electrons same, otherwise you cannot add these two equations. Now if you add it, it will be cancelled. So though this is not the full reaction, but this reaction is balanced. So here the main important thing that you have to notice is that 1 mole H2 equal to, that is when 1 mole of H2 will be produced, then 1 mole Cl2 will also be produced. That means at same temperature and pressure, as volume is directly proportional to number of moles, so their volume will also be same. Okay, so chlorine produced, that will also be 5 liters. Okay, so the first option A, that is the correct option. So sometimes numericals, when you will read first, it seems very difficult, but actually it is not so. Okay, calculate quantity of electricity that will be required to liberate 710 gram of chlorine. Now again chlorine gas, but in terms of weight, not volume, by electrolyzing a concentrated solution of NaCl. What weight of NaOH and what volume of H2 at 27 degrees centigrade and 1 atmosphere, because it is volume, so that is why this temperature, pressure that you mentioned will be obtained. So basically you have to solve three things. You have to find the amount of electricity that will be required to produce this amount of chlorine. Amount of chlorine is given, and once you are done with that, then you have to find out what is the weight of NaOH, because we know in aqueous NaCl electrolysis sodium hydroxide is produced, and also the volume of H2. So basically there are three products: chlorine, H2, NaOH. So as we have seen in the previous slide, that 2Cl minus is converted to chlorine 2 electron. Okay, and this is another reaction. So basically here, for each, as you have written 2Cl minus, that means here 2Na plus is also there, and as we have written 2H plus, that means 2HO plus will also be there. So both these together, it will make 2 moles of NaOH. So basically when you are passing 2 electron, that is 2 Faraday, you will get 2 moles of NaOH. So it is 1:1. 2 Faraday, 2 NaOH. 1 Faraday, 1 NaOH. 1:1. Now here number of that is amount of chlorine is given, and chlorine we know atomic mass is 35.5. So for chlorine molecular weight will be 35.5 into 2, 71. Number of moles of chlorine given weight divided by molecular weight, this is 10 moles. Now 10 moles electron means, 10 moles chlorine. Okay, so when you are getting 1 mole chlorine, basically it is related to number of electron 2, that means it is 1:2. So if we are getting 10 moles of chlorine, that means it involves 20 moles of electron, right? 20 moles of electron means what? 20 Faraday of charge, because 1 electron 1 Faraday. So 2 moles of electron generate 1 mole chlorine. So 20 mole, 2 moles electron generate 1 mole chlorine. 20 moles electron generate 1/2, 20. So it is 10 mole of chlorine. Okay. Now 10 moles of chlorine. So for this required charge, this is actually 20 Faraday. So directly you can do the calculation. I am doing it in detail so that you can understand it easily. But when you will actually solve this question in the examination hall, obviously to save time, try to do it as simply as possible. Okay. So you can understand that when it is 10 you are getting the corresponding number of electrons from this equation, it is 2. That means Faraday, that will also be double. So the first answer, suppose now if I am writing number 1, that is what is the amount of electricity? It is 20 into 96500 coulomb, which is 1.93, very high value. So this is the first answer. Now the second one is, we have to find the amount of NaOH. So when there is 2 electron, it is 2 NaOH. That means for production of 2 moles of NaOH, we have to provide 20 Faraday. So from 20 Faraday, we will get 20 moles of NaOH. And NaOH has molecular weight 40. If you are having trouble how it is 40, then see, it is 23 for sodium, oxygen 16, it is 40. So 20 moles NaOH means 20 into 40, 800 grams. So this is the second answer. Now the third answer, volume. So temperature given, pressure given. If volume is known, from the equation PV equal to nRT, you can easily calculate what will be the volume. PV equal to nRT from this equation if number of moles also known, because T and P both are given. This is T, this is P. You can easily calculate what will be the volume. Now number of moles you can easily understand. When 2 electron involved, 1 mole hydrogen produced. So when 20 Faraday involved, there will be 10 moles hydrogen. Now use the equation nRT by P. This is 10. R will be in liter atmosphere unit, so 0.082. Here unit is very important. That is, as it is liter atmosphere, if you use the other unit of in joule or SI system, it will be completely wrong. Temperature is 27, convert it to Kelvin, it will be 300, and pressure is 1 atmosphere. So from this calculation, 10 into 0.082 into 300, the volume you will get, answer is 246 liter. Okay, so in this way we have to solve this problem. Total 3 answers we have to find.